Good day, and welcome to this lecture on the introduction to convolutional neural networks. My name is Leen Remmelzwaal, and I'm a PhD student at the University of Cape Town and a machine learning consultant. I'd like to start by giving you a short introduction. I studied my undergraduate and master's degrees in electrical engineering at the University of Cape Town, where I am currently enrolled in a PhD in computational neuroscience. I also work as a machine learning consultant for clients around Cape Town. The projects I work on typically include object detection, for example, vehicle, OCR, which stands for optical character recognition, anomaly detection, digital biometrics, which includes both visual and user behavior biometrics, and also surveillance. I've used a selection of supervised and unsupervised learning algorithms in each of these projects, the most common of which is the convolutional neural network, which we will talk about today. Before we dive into convolutional neural networks, let us start with the question, what is a neural network? Well, the simple answer to that is that a neural network is a computer model that has the capacity to learn. It can learn from its environment, it can learn from data, and it can learn from people. Learning can be typically supervised, where you give it labeled data, or unsupervised, where you've given it unstructured or unlabeled data. There are many different neural network architectures, as you can see in these diagrams. Each one of them has a specific purpose and specific function. For example, the deep convolutional neural network has been specifically designed to classify objects. The convolution works specifically well with images. So it has been designed to classify images, as you can see in this example. The denoising autoencoder has been designed to remove noise from an image. And thirdly, the generative adversarial network, which is a rather new and popular model, also known as a GAN, has the ability to combine styles from an image with another image in order to create something new that hasn't been seen before, that combines both of those inputs into something novel and creative. In this lecture, we are going to focus on a classification network, the deep convolutional neural network. For example, this network will be able to take an image of a motorbike, pass it through the classification layers, and at the end, the output should show that we are looking at a motorbike. We're going to look at various combinations. We're going to look at a pure neural network as well as a convolutional neural network and how they respond to various variations of inputs. In this lecture, we're going to break it up into 4 parts. Firstly, how to build a feed-forward neural network. Secondly, we're going to have a look at the limitations of that neural network. Then we will explore the convolutional neural network and what it actually is. And then at the end, we will build a convolutional neural network and compare its performance to the feed-forward neural network. In this first section, we will build a feed-forward neural network. The first challenge we have is to select a data set. A data set is a publicly available set of images or other content which you can benchmark your performance against. There are 3 popular data sets available for images. We have the MNIST image dataset, which consists of handwritten digits between the digit 0 and the digit 9. They are handwritten and scanned in and then turned into images that are 28 by 28 pixels. Similar to the MNIST dataset, you also get the fashion MNIST dataset. Also, a dataset that consists of images that are square. Each one of them has an item in it, and there's 1 of 10 items. These are just examples of some of them: a sandal, a pullover, a t-shirt. In the same way that the MNIST has 10 different digits, the fashion MNIST also has 10 different types of clothing. The final one is your cipher 10, implying that there are 10 classes again. There are 10 different objects: deers, automobiles, ships, horses, birds, and a few additional ones. The only difference here is that the cipher 10 dataset consists of color, not just black and white. So there are 3 different dimensions for your red, green, and blue, which makes it a more complex dataset compared to the other 2. So for this example, I am using the MNIST dataset, the very first of the 3 datasets. As I mentioned, it's got a number of images in it. In this particular case, 60,000 images. So there are 60,000 unique images in this training set. Each one of those images is 28 by 28 pixels, and there's a total of 10 classes, which means that each image is mapped to a certain digit number between 0 and 9, so that you can train your neural network to learn what a digit is, and then you can also test it and validate to see whether what it's telling you it is in fact the correct answer. The very first layer of our neural network is a flattening layer. What we will have to do is we'll have to take an image that's 28 by 28 pixels, split it into individual rows, and then concatenate those rows in such a way that we have a 1D array. A standard neural network is not designed out of the box to handle 2D arrays, and therefore we need to flatten it into a one-dimensional array. The one-dimensional array, if we have 28 by 28, the one-dimensional array will then be 784 elements by 1. So there'll be 1 element in each one of those placeholders. We look at the output layer. As I mentioned, there are 10 digits between 0 and 9. However, what we want is, instead of a single output, I'd like to actually classify these as 10 different classes. And the way of doing that is using a binary class matrix, meaning that your output layer consists of 10 digits, and each one of them will be flagged in turn if it represents that digit. So if it is a digit 0, the first element on the output will be raised. If it is a digit 1, the second element would be raised. This doesn't mean it has to be exclusive. Only during training do we keep it exclusive. In testing, you'll notice that multiple output classes will be raised for a specific digit. For example, a 6 might look very similar to an 8. So when the 6 is raised, you might find that the 8 is also raised slightly because it might be one or either of the 2. In this neural network design, we have then taken our 28 by 28 image. We have flattened it into 784 units. I have then created a hidden layer of 512 units, and that will feed into your final output layer of 10 units, each one of them representing a different class. So here in this neural network model, we have a 784 leading to 512 leading to 10. So this is what we call a 3-layer neural network. This is the implementation of that. The very first layer is a flattening, followed by a dense layer, followed by a second dense layer, followed by your output. On the screen, we show the progress during the training of this neural network. What we've done with the image dataset of 60,000 images is we've split it into 2 different datasets. We have our training set, which is the majority of the images, in this case 50,000, and I've split it out into a second testing set, which is your 10,000. So this training is taking place across the 50,000, the larger of the 2 sets. And what I've done is I've run this through each one of those images 5 times. And what that's called is an epoch. There are 5 epochs. And what that means is that all those images, 50,000 images, have been run through the network 5 times each with the labeled data, trying to teach this neural network what each of those digits should be. As you can see here with the blue line represents the accuracy. The dark blue line, the solid blue line, is on your training set. Your dotted blue line is on your validation set or your testing set. And really, this is what we want to look at as your overall performance. As you can see, at the end of 5 epochs, we have managed to achieve 98.1% accuracy. And what this means is that every item in the testing set that is never seen before during the training managed to achieve the correct classification 98.1% of the time, which is really, really fantastic for a feed-forward neural network on such a large data set. Here's an example of the output. I fitted each one of these images. Here's a sample of 9 of them. This is the class that it thought that image belonged to, and I've highlighted with green when they're correct. And as you can see, all 9 of them in this example are correct. In the second section, we will now talk a little bit about the limitations of neural networks and why we need to move to a convolutional neural network. The really interesting part happens when you start applying what we call augmentations to an image. Why this is important is that the number 7 or the number 4 or the t-shirt or the dog, whatever you're looking at, will not always be in the middle of the frame looking at you perfectly, the way that you've trained it. Images tend to be augmented. Images are not always in the middle of the frame. There are 5 typical common augmentations that can take place. The first one is the scale. An image could be slightly larger than what you've trained it or slightly smaller than what you've trained it for. There could also be a shift, either vertical or horizontal, meaning that the image is slightly higher in the frame or slightly lower, slightly more to the left, slightly more to the right. There could also be a rotation. A rotation is when the image rotates a certain number of degrees. And finally, a shear, which means the image could be leaning more to one side or sheared. For example, here is the original 7, and the augmentations I've applied to this, in this case here, there's a vertical drop where the image is much lower in the frame. Here it's slightly on the right. In this one here, the image has been rotated and moved to the right and moved up. So there are multiple augmentations taking place to these images. And now what we're going to do is we're going to take these augmented images and see how well the neural network can classify these augmented images. Well, here we go. I've highlighted in green the ones that they've gotten right, and I've highlighted in red the ones that the neural network failed on. It misclassified those. In this case, I thought it was an 8. In this case, I thought it was a 3. The reason here is that there is an incredible inherent weakness in the neural network, especially in the feed-forward neural network, and that is that it does not handle augmentation very well. In the second section now, we will talk about what is a convolutional neural network and how can you solve some of these problems with this new architecture. Alright, so in designing a neural network, let us compare it to the standard neural network we designed earlier. In the standard neural network, we had an image like a motorbike being passed through into the classification neural network, which would then tell you that this is a motorbike we are looking at. What is different about the convolutional neural network is that we introduce a new layer. We introduce a layer that is specifically responsible for feature extraction. It doesn't pass the entire image through to the classifier. It passes the image through to a feature extraction algorithm or a feature extraction layer, which then passes individual features to the classification layer. What this means is that instead of receiving a motorbike on the classification layer, you receive a wheel, a fairing, a spoke, a component of the entire image, which allows the classifier to then calculate whether an image is there based on its components and not based on the entire object. An example of feature extraction in this case is shown with a 3-level of feature extraction. 3 levels are quite common, and we will use 3 levels in these examples today. 3 levels means that it extracts features at a low level. These could be lines, vertical lines, diagonal lines, horizontal lines. They could also be colors. These are then combined into what is called a mid-level feature. These are then combined into what is called a mid-level feature. A mid-level feature consists of various low-level features combined into something more complex. And what you start seeing here is you start seeing patterns and textures arising. Swirls, lines, almost like a zebra. And finally, these and combinations of mid-level features get passed into your high-level features. These will be your swirls, these will be your forelegs for an animal. These will be various high-level components that might belong to the image. So just to summarize, low-level features are extracted from the original image, mid-level features are combinations of low-level features, and high-level features are combinations of mid-level features. It has also been known that CNNs are very good at extracting textures. So for example here, this has been trained to pull out the texture of an Indian elephant, and in this case the object of a cat. But if you pass it through the same image of a cat, but given the texture of an elephant, it actually prefers the texture rather than the object. So it is biased towards texture, in this case here. All right, typical neural network layers for the convolutional neural network consist of three. You have your convolutional layer, your max pooling layer, and your dropout layer. Now what typically happens is these three are clustered and repeated. So you'll have three groups of three layers. So a neural network, convolutional neural network, could have an additional 9 layers, of which we consider these 3 convolutional layers. Let's have a look at each one of these 3, convolutional, max pooling, and dropout, in a little bit more detail. The first one we're looking at is the convolutional layer, and this is really the powerful engine behind convolutional neural networks. As you can see here in this illustration, the original image, which is sitting on the floor in blue, is being projected up through what is called a filter. A filter is a small grid, sometimes 3 by 3, sometimes 5 by 5, that is passed across the image, as you can see here. When that image matches a certain feature, it projects up into what is called a feature map, and that feature is then highlighted. So if it notices, for example, a wheel in the bottom corner here, as soon as the filter goes over those 4 squares and identifies a wheel, it will project up into this quadrant here and inform the feature map that they have detected a specific feature. The second layer we're going to have a look at is your max pooling layer. A max pooling layer allows the network to reduce its dimensionality. Convolutional layers tend to expand dimensionality, so max pooling layers are designed to reduce it. The max pooling will take the sum of a group, so this one here is a 2 by 2 grid. It will find what is the highest number in that grid. So a 7, a 3, a 7, and an 8. The 8 is the highest. It will then take the 8 and project it here into this quadrant over here. So what it's doing is it's taking a 4 by 4 grid, converting it to a 2 by 2 grid, but still maintaining the maximum values from each one of these grids. So the information is still maintained, but the dimensionality is reduced. The third layer is your dropout layer. The dropout layer is shown here, where on the left-hand side we have a fully connected neural network with 1, 2, 3 layers and an output layer. After the dropout, what has happened is there are certain nodes in the layer that have actually been removed, and therefore all connections that correspond with that node, everything leading to the node, everything leading from the node, have also been removed. It is a pruning, it is a removal of connections from the neural network. There could be multiple reasons for this. One could be that the connections were very, very weak originally and didn't serve any strengthening purpose and therefore were removed. But there could be other reasons as well. And this brings us to our last section of this lecture. How do we build a convolutional neural network? And what do those effects look like when compared to your standard feed-forward neural network? Here's an example of the implementation in a software program called Keras. You'll see here in the dotted blue lines, we have all of the convolutional layers we've spoken about. We start off with our convolutional layer, followed by our max pooling layer, and at the end we have a flattening layer before it gets passed into the classification. Here again is another one of those training diagrams, which shows how the neural network trains. What we've done here is, again, 5 epochs. Here's the first one, the second one, the third one, the fourth one, and the fifth one. And as you can see here with the dark blue line, this is the information we gave it during the training. So this is the validation, this is the training score. So the training score is actually lower, the validation score is actually higher, which is what we wanted. And we can see an overall accuracy here of 99.2%. Let's have a quick look at the results. So what we've done is initially is we've passed it through data that was part of the original MNIST dataset, which has not been augmented. What we have done here is just taken those images, passed it through the convolutional neural network to see what it will classify this as. And if we have a look here, we get 9 correct boxes, just like we had with the neural network. This one classifies as 4, another 4, another 1. With this feed-forward neural network, as soon as we augmented the data, we found that there were failures across the board. Let's have a look at how it responds now with a slightly different convolutional neural network architecture, and we get a full set of accurate results. The convolutional neural network is able to handle these changes that we did not see handled by the standard neural network. So horizontal and vertical shifts, rotations, and those sort of augmentations. Here's just an example of a attention map, or the ability to visualize that. The red areas in the diagrams indicate areas that are of interest to the convolutional neural network, areas that it took into account when trying to classify this object. Here you see this particular part of the 6 was very important. If it saw that and it saw this over here, it would use those features to classify it as a number 6. Same thing with the 4, same thing with the 2. And there's various other tools that you can use to help understand what the convolutional neural network is doing. These are just some of them. In summary, what we've shown today is that a convolutional neural network adds an additional layer known as the feature extraction layer. This could consist of multiple layers, the convolutional layer, the max pooling layer, as well as the dropout layer. But there's a whole new function that is added. It looks for features within an image rather than just the image itself. We've spoken about a 99.2% efficiency. What you can also see that as is a 0.8% error. So here we have what is known as the MNIST benchmark scores. There's a link there to have a look at, benchmarks.ai/MNIST, and you can have a look at all of the different types of models that people have used in order to get a higher accuracy. In this case, they want to reduce the error, and the best one at the moment is the 0.21%. I don't think you can get much higher than that, mostly because there are a few mislabeled images in the data set, which is why it's not possible to get higher than that. So I think this is mathematically as high as is possible. And as you can see, this was achieved in 2013. And here is the paper. If you click on this link, it will take you to the paper that describes the model that achieved that high level of accuracy. But if you have a look on the right-hand side here, here's an example of one of the architectures. Each one of these is its own convolutional layer. 1, 2, 3, 4, 5, 6. You've got at least 10 or 15 convolutional layers, where we have only used 3 in today's lecture. Thank you very much for listening to this lecture. What we've done today is we've spoken briefly about convolutional neural networks. And please feel free to contact me or your lecturer if you have any questions about that.